So this recording is going to be the first screencast for a new chapter, chapter 3 in your textbook called Matter, Properties, and Change. So chemistry, if you remember, is the study of matter and energy. So this chapter is going to deal primarily with the substance side of matter, of chemistry, the matter part. But we are going to talk a little bit about energy in a couple of the next two screencasts. So the first thing we're going to look at is an overall chart showing the organization of matter. So if all matter is broken down into these categories, you have two big categories. You have mixtures and pure substances, and there's physical changes that can take you back and forth between these two mixtures. So think about a mixture of sand and water, right? How would you separate the sand from the water to get the pure sand and the pure water? Well, you could filter it. That would be one way. So that's a physical process. It doesn't change the composition of either substance. And then under each of these two big categories, we have two categories. Under pure substances, we have elements and compounds. We're going to talk about each of these in a second. And then under mixtures, we have what are known as heterogeneous mixtures, also sometimes called suspensions, or homogeneous mixtures that are also called solutions. And to get back and forth between elements and compounds, chemical bonds have to be broken or formed. So that's where we get into the idea of chemical change. So the first type of substance we want to talk about is an element. So remember, the pure substance side of the chart up there had elements and compounds in it. So an element is defined as a pure substance made up of only one type of atom. And when you look at the symbol for an element, like gold, for example, the symbol will be either one or two letters, but it will always begin with a capital letter. So you'll have one symbol, element symbol, that represents an element. And here's a picture of gold. You can see that it's very uniform. You can tell that it's one substance throughout. Another example would be oxygen gas. The symbol for oxygen gas is a capital O. It's often written as O2 because it actually exists as two little atoms of oxygen stuck together, but still just one symbol, one type of atom, so that makes it an element. It's a pure substance. Oxygen, you might know already, is a clear, colorless gas, right? So we can't really see what oxygen looks like. If we look at it, it looks invisible, but it would be uniform, looks the same throughout, just like any other type of element. So the elements are organized in the periodic table. There are 92 naturally occurring elements on the planet. Anything above number 92, which is here uranium, is actually what we know as synthetic elements. They've been made in nuclear reactors, or like the really heavy elements don't even exist yet. But elements are all represented by symbols. And so that's how you can tell if you have a pure element, because it would just be one symbol, meaning one capital letter and one lowercase letter, or just one capital letter, like K over here, or H. So compound is the next type of matter. You might think of it as the next most complicated type of matter. It's made up of at least two types of elements bonded together. So two or more types of atoms bonded together. And how do we know if we have an element? Well, it's going to have two different chemical symbols in it. So here we have the symbol Fe with one capital letter, and we have the symbol O with its own capital letter. We know that that's iron 3 oxide. So that's a compound made up of iron and oxygen. Here's what it looks like. Pretty uniform looking, right? All one color. You could imagine if you were looking at the smallest particles, they would all kind of look the same. It's a little bit clumpy around the edges, but still uniform in appearance. And then water is another very common example of a pure substance known as a compound made up of hydrogen and oxygen, H2O. You can tell it's two elements because it's two capital letters representing two different symbols. So you have, again, very uniform in appearance, a clear, colorless liquid. So mixtures make up the other side of the matter chart. A mixture is very simply a combination of two or more substances in which each substance retains its individual chemical properties. So here's a very obvious mixture, M&M's trail mix, M&M's and granola and raisins. And here's another mixture you might not think about. Kool-Aid, it's a mixture of water and the sugar and the Kool-Aid powder, which is flavoring and coloring, but all mixed together. We could eventually separate all this out if we had to, using different methods of separation. So there's one type of mixture called a heterogeneous mixture. And these are mixtures where the appearance is not uniform. Each substance retains its distinct color, sometimes properties. Here you can see that in this granite, you have different minerals within the granite that retain their own identity. Fog, or this contrail coming out of this plane, or clouds, the reason they appear the way they do is because the water droplets are maintaining their own identity against the gas of the atmosphere. So fog is another example of a heterogeneous mixture, which these are also known as suspensions. And I have this picture here. This is children's Motrin. And you can see right on the package, it says oral suspension. And if you look a little bit more carefully, you know that it has more than one substance in it because it has 100 milligrams per teaspoon of the active ingredient, ibuprofen. And it also has, down here, you can see the strawberry flavor. So you know at least it has strawberry flavoring in it. Here it says berry flavor up here. And there's a whole bunch of other stuff in there as well. But if you try to look through it, it's cloudy. You can't see through a suspension or a heterogeneous mixture that is in the liquid state, because it becomes cloudy because the particles are too big to let light pass through. So other examples of liquid suspensions would be things like milk or salad dressing or things like that. So homogeneous mixtures, by comparison, are completely uniform. Okay, so they're still made up of two or more types of substances that retain their own identity, but they don't look like it. They look like a pure substance. So this is an alloy of titanium, which is a mixture of metals, but they're mixed at the atomic level. So when you look at them, they appear completely uniform. They're also called solutions, and they could be solid like this alloy. They can be liquid like this pool water. They're clear because it has, but we know that it has chlorine in it and it has some other pool chemicals plus the water molecules, right? And then if it's a gas, they're also going to be completely clear and completely uniform. So the air around us is a solution. It's made up of nitrogen and oxygen and carbon dioxide mostly. But when you look at it, you can see right through it. It's completely clear. And here's another example of a solution, a liquid solution. And this time you can actually see through it. This is children's Benadryl. And you know that it has more than one substance, again, because it has the active ingredient here and the flavoring. It has other, you can imagine it must have water in it as well. But look, if I try to look through it, I can actually read the words on the page right through this mixture, because it's a homogeneous mixture, which means it's a solution. So if you have solutions that are liquid or gas, they're going to be totally clear, not cloudy. So another way to think about matter are the states that matter will exist in nature. So there's 3 states of matter that exist on the planet: solid, liquid, and gas. And these are things that you guys should be really familiar with at this point. So this is just a quick review. If you think about the characteristics of solids, they have a very definite shape. They have very definite volume. You can't compress solids. You can't make them take up any less space. And the particles, as you can see in this picture, are very, very tightly packed. Liquids, on the other hand, have no definite shape. They can take the shape of their container. They do have a definite volume, so you can't compress a liquid. You can't make a pitcher of water, if you push down on the top of the water, take up less space. And the particles are still pretty close together, but just far enough apart that they can slide past each other, which is why liquids have that ability to flow. But then gases are the highest energy and the particles furthest apart of the 3 states of matter. They have no definite shape and no definite volume. So what we say is they take the shape of their container and the volume. They fill the volume of whatever container they're in. They are compressible. So you could imagine if you could push on all sides of this cube with enough pressure, you could get those gas particles to take up less space by pushing them closer together. And that's unique to gases. They're the only state of matter that is compressible. And the particles in gases are moving faster and are further apart than in the other 2 states of matter. So the last thing we're going to look at today are the different ways of describing matter. And there's 2 main categories in the properties of matter as well. So matter, as you know, is anything that takes up space and has mass. And here are just some examples of different forms of matter. We have salt, we have water again, and a different sample of gold this time. And these are all known as pure substances, if you remember from that chart at the beginning. So one way to describe the properties of matter are using physical properties, which are characteristics of matter that can be observed without changing the sample's composition. So things like density, which we've already studied, and melting point and boiling point, color, odor, taste. Those are some qualitative physical properties. Think about water. What are some of the ways that you would describe water? What's its boiling point? What is its melting point? Okay, those are all physical properties. Here are some physical properties of common substances. And again, what state it's in at room temperature is a common physical property, and then the other ones that we've talked about. And you can see how gases have very, very low densities in general compared to solids and liquids that are listed below. There are two types of physical properties. There's extensive physical properties, and these are the ones that depend on amount. So the really obvious ones that we've already been measuring in class, like mass and length and volume, right? If I have a certain amount of water in a pitcher, I can measure the volume. If I add more water to the pitcher, it's going to be more volume. That's called an extensive physical property. An intensive property is one that doesn't depend on amount. So density, for example, is intensive. It's always the same for any sample of a substance because that ratio of mass to volume remains constant. Melting point is another intensive property. Doesn't matter if you have a drop of water or a bucket of water, it's still going to melt at 0 degrees Celsius. And these are some more examples of intensive properties. So the last type of property we're going to talk about for describing matter are chemical properties. And these are different because they describe the ability of a substance to combine with or change into one or more other substances. Okay, so you can't observe a chemical property without actually changing the identity of the substance. So here's two examples of chemical properties. Iron will form rust when it is exposed to air, right? That's a chemical property because you can't see that iron will rust until it actually changes into iron oxide. And methane, which is a colorless gas, will burn in the presence of oxygen. Okay, so that's another one. You can't observe that chemical property until you see methane burn, give off a flame, and change into carbon dioxide and water. So here's a table that just compares some of the common physical properties of copper down one side and the chemical properties down the other side. So here's the check for understanding. Write these down on your summary sheet. Density is what kind of property? Is it an atomic property, intensive physical property, an extensive physical property, or a dependent property? And what defines a gas? Do gases have a definite volume and shape? Do they have a definite volume but take the shape of their container? Do they have no definite volume or shape? Or do gases have a definite shape but no definite volume? Okay, so that's it for today. Make sure you have any definitions that you need written down from the list at the bottom of the page, and make sure you have the questions from the summary sheet answered in your notebook.